Hello, physics students. Welcome. We're going to take a look at some problems now dealing with collisions. Let's get into it. So we went over this last time, the types of collisions, elastic and inelastic. The main thing is that the conservation of momentum in all types of collisions is always there. The momentum before the collision is going to be equal to the momentum after the collision. Only in elastic collisions, kinetic energy is also conserved, where in inelastic collisions, some of the kinetic energy is lost, either into the changing shapes of the objects or other forms of energy. All right, so let's take a look at a problem. Okay, so a dart traveling at 80 meters per second is impaled into a wood block that is at rest. What is the final velocity of the wood and the dart? All right, so let's start with my drawing here. So I've got a dart and a wood block. So the dart, we'll call that V1I, is at 80 meters per second. And V2I is 0. This object is at rest. The block of wood is 0.5 kilograms. And the dart, don't get caught, 50 grams. Got to divide that by 1,000. So 0.05 kilograms. So this is my initial conditions. So this is my initial momentum. And over here is going to be my final momentum. It's a little rough row there. But in the final momentum, the word impaled means it comes stuck together. So this is a perfectly inelastic collision. Okay, because the two objects become stuck together and travel as one, this is a perfectly inelastic collision. So my dart is impaled and the two objects travel off as one. So over here, my initial momentum, m1 v1I plus m2 v2I is going to be equal to, now, since these two become stuck together, they act as one. It's going to be m1 plus m2 times v2. All right, we don't need a v2 there. Sorry, let's get rid of the v2. It's just let's get it right. I'll go back and fix my drawing. M1 plus M2 times VF. So let's think about this VF. This is the only object that had momentum. This object had zero momentum because it had zero velocity. So these two together are going to have a smaller velocity than this 80 meters per second because the mass increased. Okay, so if we get a number not smaller than 80, we know we've got something wrong. All right, so let's take a look at the problem here. Let's put some numbers in. So 0.05 times 80 plus 5 times 0. That's going to be 0. equals 0.05 plus 0.5. Should I get my 0.5 over there? VF. Okay, a little calculator action here. So 80 times 0.05 is 4 plus 0. That's 4. It's going to be equal over here to this side. 0.55 VF. So 4 equals 0.55 VF. Divide both sides by 0.55. And we get a VF equal to 7.27 meters per second. So as we thought, a much lower velocity because this momentum of the dart has to now provide all the momentum for both the dart and the block of wood. Okay. So anytime this object's at rest and as they stick together, the final velocity is got to be less than that initial velocity if the second one's at rest. All right, let's take a look at one more quick example. Let's get this a little bigger so it's a little easier to see. I go more space to write. All righty, here we go. A golfer swings a 0.675 kilogram driver with a club head speed of 38 meters per second. If the mass of a golf ball is 0.05 kilograms, what's the velocity of the driver after impact if the velocity of the ball after impact is 55 meters per second? And what type of collision is it? All right, so I know you've missed my artful drawings. There's my golf club. There's my golf ball. This is M1. This is M2. We know that initially V2I is 0, right? The golf ball is at rest. And V1I, the golf club, is traveling with a velocity of 38 meters per second. Okay, so again, this is the initial conditions. Let's take a look at the final conditions. Okay, so what happens when a golf club hits a golf ball? Do they stick together? No, right? So the golf ball goes flying off. And in this case, with a velocity of 55 meters per second. But does the golf club stop? No, it continues going off in this direction at some unknown final velocity. So that's what we're trying to find out. Okay, so the second question, what type of collision is it? We know it's not perfectly inelastic because they don't stick together. So it's either going to be elastic or inelastic. We're going to have to take a look at the kinetic energies to see what happens, to see if it remains, if the kinetic energy remains the same on both sides, then it's elastic. All right, so let's take a look over here. We got M1 V1I plus M2 V2I equals m1 v1f plus m2 v2f. Okay, so the mass of the driver, 0.675 times the velocity of the driver, 38, plus 0.05 times 0. That's going to equal 0.675 v1f plus 0.05 times 55. Okay, time for calculator. So on the left side, we have 0.675 times 38. That's going to give us an initial momentum of 25.65 spears and 0.675 v1f plus 0.05 times 55 gives us 2.75. So subtracting the 2.75 from both sides, we're going to have 22.9 equals 0.675 v1f. Now let's think about this. If this object has momentum and this object has no momentum, and in the end, this object has momentum, the golf ball now has momentum, where'd it get it from? That's right. The golf club lost momentum. So it's got to have a velocity lower than this 38.5 meters per second, right? It transferred during the impact, right? There was an impulse that the golf club gave to the golf ball. So the golf club lost momentum. The golf ball gained momentum. But the total is going to stay the same. So if this velocity's got to be lower than 38. If it's not, we've got a problem. So I take that 22.9 divided by 0.675 and come up with a final velocity of the golf club of 33.93. 33.93 meters per second for the final velocity of the golf club. So yes, the golf club did lose some speed, its velocity, because it lost some or transferred some of its momentum to the golf ball. So now, what type of collision is this? Well, there's only one way to answer that question. We got to look at the initial kinetic energy of the system and the final kinetic energy of the system, right? So over on this side, we have 1/2 m1 v1 I squared. All right, that's the initial kinetic energy of the golf club. The golf ball has 0 kinetic energy. So I'll just put that 0 in there. And over here on this side of the equation, we're going to have 2 objects with kinetic energy. m1 v1f squared plus 1/2 m2 v2f squared. Well, I'm going to need that final velocity later, so let's not erase it yet. We'll just have to work around it. Now let's go to a different color so maybe we make sure we see it. Okay, so over here we have 1/2 times 0.675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 . 675 times 38 squared. So the initial kinetic energy, let's just do that, 0.5 times 0.675 times 38 squared gives me initial kinetic energy of 487.35 joules. I'll come down here and do the final kinetic energy. 1/2 times 0.675 times 33.93 squared plus 1/2 times 0.05 times 55 squared. Sorry, my handwriting is getting a little sloppy there. All right, so let's do that. 0.5 times 0.675 times 33.93 squared plus 0.5 times 0.05 times 55 squared. Gives me a kinetic energy after the interaction or collision of 464.17 joules. So there was a loss of a little bit of kinetic energy. It's close to being elastic, but not exactly, because that ball gets a little deformed. You obviously hear a noise when the two make contact. So it's not quite, so you would have to call this an elastic, or I'm sorry, it's not an elastic collision because of the loss of kinetic energy. It's an inelastic collision. Okay, so there's two examples. There's a set of problems to go along with this. Again, the top 4 problems are back to the impulse and momentum, change in momentum. That whole formula from before, Ft equals J, the impulse, which is equal to the change in momentum, delta rho, which is equal to the change in, or the mass times the change in velocity. Okay, so that's the top 4 problems. And then there's some problems dealing with collisions that you can deal with. All right, good luck and stay safe. If you have any questions, please contact me and keep up the hard work. I appreciate all the hard work that you guys are doing. We only got a little bit of time to finish up. Let's